Okay. So in last class, I have given you exercise. In this exercise, there are 4 questions. The first question was, you are supposed to obtain Fourier series for this function e raised to the power minus x in the interval 0 to 2 pi. This is your given function fx is equal to e raised to the power minus x in this interval, and let the Fourier series for this function, Fourier series expansion for this function be this one, a naught by 2 plus summation an cos nx plus summation bn sin nx. So first we want to find the value of a naught, and if you remember, the formula for a naught is 1 over pi integration a to b fx dx. Okay, the integration of function from the limits a to b. In this case, the limits are from 0 to 2 pi. So it will be 1 over pi. From 0 to 2 pi, I want to integrate the function e raised to the power minus x dx. Okay. So the integration of this function will be e raised to the power minus x divided by minus 1, and the limits will be 2 pi to 0. So if I insert the limits in this integral, will be 1 over pi. Okay, I am taking the minus outside. Minus 1 over pi e raised to the power minus 2 pi minus e raised to the power 0, that will be 1. So my a naught becomes 1 minus e raised to the power minus 2 pi. I am adjusting that negative here. 1 minus e raised to the power minus 2 pi divided by pi. Okay, so this will be your value of first Fourier coefficient, that is a naught. Okay. Similarly, we can also find the value of an as we know, value of an is given by the solution of this integral. Okay, and of course in this case the limits were 0 to 2 pi, so I will just insert the values of limits as well as the function. 1 over pi 0 to 2 pi e raised to the power minus x dot cos nx and dx. So for solving this type of integral, there is a simple formula. This one. So e raised to the power ax dot cos bx dx will be equal to, the integral of this will be equal to e raised to the power ax divided by this much. So in this case, if I correlate with this formula, then I will get my a is equal to minus 1 and my b is n. These formulas you have to remember by yourself. You cannot derive this, or you cannot even solve this integral very easily without the help of this type of formulas. So if I insert the integral value, if I solve the integral with the help of this formula, what I will get is an will be equal to 1 over pi and e raised to the power minus x over 1 plus n square into minus cos nx plus n sin nx in the limits 0 to 2 pi. Okay. If I insert this formula, if I use this formula, this integral will simplify to this one. So this an becomes 1 over pi 1 plus n square. I am taking 1 plus n square outside, and for limit purpose, I will do this n e raised to the power minus x sin nx minus e raised to the power minus x cos mx. Okay. So if I insert the limits in these particular expressions, then okay, let's start inserting the upper limit first. It will be n e raised to the power minus pi minus 2 pi sine 2n pi, okay, minus n e raised to the power minus 0 and sine 0 minus minus e raised to the power minus 2 pi cos 2n pi minus e raised to the power minus 0 and cos 0. Okay. So this was your an. As you can see from here, I will be using these trigonometric identities here. Sine 2n pi will be 0. Similarly, sine 0 is 0. Cos 2n pi is plus 1 and cos 0 is also 1. So if I insert these identities in this particular expression, then it will look something like this. An is equal to 1 over pi 1 plus n square 0 minus 0 in this case. Both the terms will be 0 because it is sine 2n pi and it is sine 0, and minus e raised to the power minus 2 into 1 minus 1. Okay. So the value of my an becomes, I can write 1 over n square plus 1 into 1 minus e raised to the power minus 2 pi. I am adjusting the negative sign here, divided by pi. Okay, so an value becomes 1 over n square plus 1 into 1 minus e raised to the power minus 2 pi divided by pi. Similarly, we can also find value of Bn. Now, the integral for Bn is fx dx from limits a to b. So, in this particular question, it will become 1 over pi 0 to 2 pi and the function itself. Oh, sorry, sin nx dx was there. Okay, again, I will be using the same formula. Okay, let's insert that formula again. I will be using this formula, e raised to the power ax dot sin bx dx will be equal to this much. In this case, if I relate with my original expression, then I will see my a is equal to minus 1 and my b is equal to n. So if I insert this, if I use this formula to solve this integral, then the value of bn will become 1 over pi e raised to the power minus x 1 plus n square into minus sin nx minus n cos nx. Of course, the limits was from 0 to 2 pi. Okay, so I can write this minus 1 over pi 1 plus n square. I am taking negative sign outside, and it will be e raised to the power minus x sin nx plus n e raised to the power minus x cos nx. So if I insert the values of if I insert the upper limit and lower limit to this expression, then and by using that identities, sin 2n pi is equal to 0, sin 0 will be 0. Similarly, cos 2n pi and cos 0 are 1. So I will get Bn is equal to minus 1 over pi 1 plus n square 0 minus 0, sin term will be 0 plus, while cos terms will be n e raised to the power minus 2 pi minus simply n. So my Bn will become n over, I am taking n outside from both the terms, n over n square plus 1, and I am adjusting the negative also, 1 minus e raised to the power minus 2 pi divided by pi. This will be my expression for my Bn. Okay. So if I insert this Fourier coefficient into my Fourier series expansion, then my Fourier series will become the function e raised to the power minus x can be represented like this: a naught, which was 1 minus e raised to the power minus 2 pi, divided by pi, but in formula we have a 2 extra, so it will be something like this, plus summation and the value of an, which was 1 minus e raised to the power minus 2 pi divided by pi into 1 by n square plus 1 and cos nx plus summation n 1 minus e raised to the power minus 2 pi over pi into n upon n plus n square plus 1 into sin nx. Okay. So if I insert the if I open up this summation, then this e minus x, that is the function, can be written as 1 minus e raised to the power minus 2 pi over 2 pi. This thing I am taking common, 1 minus e raised to the power minus 2 pi, as it is, as this term is in all the three expressions, so I can take out the common, and it will be 1 plus 3 half plus, okay, if I insert n is equal to 1 here, then it will be 1 plus 1. Okay, 1 square is 1, 1 plus 1 is 2, so it will be cos x divided by 2. For second term, that is n is equal to 2, it will become 5, 1 over 5. So cos 2x over 5. Similarly, for n is equal to 3, it will be cos 3x divided by 3 square is 9, 9 plus 1 is 10. And for second expression, it will be sin x by 2. Please mute yourself if you are not asking anything. It is 2 sin 2x divided by 5 plus 3 sin 3x divided by 10. So this was required solution.
Excuse me, sir.
Yes.
Sir, ये common out e की power 1 minus c की power minus 5 by 2 upon pi आएगा sir.
Sir, only pi.
Okay.
Sir, only pi आएगा.
Yes. Sorry.
नीचे sir.
Yes.
Yes sir.
Okay. So this was your required solution. Okay. In this question, they may ask for any identity, and for that you may be for like x is equal to 0. If you put x is equal to 0, then it will this particular solution will give you some identity that you have to see for which particular value of x you can get any particular identity. Okay. So from that exercise, this was your first question. Second question I will take up a little bit later, but before that we will go to third question. Okay. First I want to discuss third question, and then we will go to second question after that. As you can see, the third question was, you are supposed to find Fourier series extension for this function 1 minus cos x. See, in these type of questions, they may ask for some different type of function like this one, root 1 minus cos x. But see, the methodology used to find a naught, an, bn, if you are master in this methodology, then you can solve for any function. Okay. But of course you have to keep in mind some trigonometric identities which will be very helpful in solving this type of question. So for this particular question, if you recall, this cos 2x is equal to 1 minus 2 sine square x. Okay. I will modify this identity. I will modify this particular identity to simplify this type of function. Okay. So this 2 sine square x can be written as 1 minus cos 2x. Okay. And if I take half of this argument, then it will be 1 minus cos x. And if I take square root of this expression, it will be sine x plus 2 divided by root of 1 minus cos x. So basically this function root of 1 minus cos x is equivalent to this function root 2 sine x by 2. Okay, and this one is simplified version of this expression. So instead of finding Fourier series expansion for this function, I can simply find expansion of this function. Okay. So again, I will be finding a naught, which will be equal to 1 over pi 0 to 2 pi. Now I am directly writing the function instead of writing fx, and in then and next step I will be writing function value of function. But in exam you have to write the general expression for a naught first, and then you have to write then you have to insert the value of function. Okay, see, in exam you have 180 minutes, so on an average for answering 4 questions you can take at least 40 minutes for each question. Okay, so please do not miss the steps, attempt all the steps, attempt the question step by step. So it will be root 2 sine x by 2 dx. This will be equal to root 2 or pi minus cos x by 2 divided by 1 by 2, and limits are 2 pi to 0. Okay, so this will become 2 root 2 or pi. This 2 is coming from the denominator half. 2 root 2 or pi. Okay, and I am also taking the negative sign outside, and this is cos x by 2 in limits 2 pi to 0. So it will become minus 2 root 2 or pi and cos pi minus cos 0. So it will be minus 1 and minus 1 both. It will be cos pi is minus 1, cos 0 is 1. So it will be minus 2 root 2 or pi minus 1 minus 1. So it will become 4 root 2 over pi. Okay. So the value of a naught is 4 root 2 over pi. Similarly, I have to find the value of an and bn also. So for an, it is 1 over pi root 2 sine x by 2 cos nx dx, and limits were 0 to 2 pi. Okay. I can take out this common root 2 over pi and integral 0 to 2 pi this sine x by 2 cos nx dx. And for this type of integral, how I can simplify this expression? So this particular trigonometric relations can be used. Okay, see, I have 2 cos a sin b will be equal to sin a plus b minus sin a minus b. So I will multiply and divide it by 2. So it will be root 2 over 2 pi, and this 2 I will compensate by multiplying it in numerator 2, and I am writing cos term first, cos nx sin x by 2 dx. So now this integral is looking like this one. So I can simply write sin a plus b minus sin a minus b instead of this. Okay. So this will become, okay, 1 over root 2 pi. Okay. This will become 1 over root 2 pi. And this integral sin n plus half x minus sin n minus half x dx. So now this is simpler, and this is a simple term, linear term in sine function. So I can easily integrate this one, 1 over root 2 pi integration of this sin n plus half x will be minus cos. Okay, I am just taking the LCM here. This will be minus cos 2n plus 1 by 2 divided by 2n plus 1 divided by 2 and x plus cos 2n minus 1 divided by 2 divided by 2n minus 1 divided by 2 x, and the limits were from 0 to 2 pi. See, the integration of this sine function will be minus cos, but that minus and this minus is, I am converting into a positive. But for this minus, this will remain a negative sign here. This will create a negative sign here. So for this, what I can do is 1 over root 2 pi minus 1 divided by 2n plus 1. Okay, I am taking this 2 outside. Minus 1 divided by 2n plus 1 into cos 2n plus 1 pi. I am also inserting the limits 2 pi to 0 minus cos 0. Okay. So this expression is simply becoming this expression after inserting the limits. Similarly, this expression will become this one after inserting the limits. So this will become plus 1 over 2n minus 1, 1 over 2n minus 1 into cos 2n minus 1 pi minus cos 0. Okay. So this term 2n plus 1 pi is equal to 1 is equal to minus 1. Similarly, this cos 0 is also minus 1. So what I can do is, next page please. So this an will become root 2 over pi 2 upon 2n plus 1 minus 2 over 2n minus 1. I can take out this 2 common, 2 root 2 pi, and it will be 2n minus 1 if I take the LCM minus 2n minus 1 divided by 4n square minus 1. So this value of an will become negative 4 root 2 over pi multiply by 4n square minus 1. Okay, so this was my value for an. Later on, I will just insert the value of n from 1 to infinite, and then we will see how this expression goes. Similarly, if I want to calculate the value of bn, it will be 1 over pi a to b. Okay, now I can directly write 0 to 2 pi 0 to 2 pi, and it will become root 2. If I insert my function here, root 2 sine x by 2 dot sine nx dx. So again, if I use my trigonometric identity for this term, so for making this identity, what I need to do is I will again multiply and divide by 2. It will be 1 over 2 pi. Okay, root 2 be here, and it will be 2 sine nx dot sine x by 2 dx. So if I use this identity, this one, it will become the bn will become 1 over root 2 pi integral cos 2n minus 1 by 2 minus cos 2n plus 1 by 2 x. Okay. So if I integrate this term, now I can simply integrate this term. This will become 1 over root 2 pi sine 2n minus 1 by 2 divided by 2n minus 1 by 2, and the integration of this second term sine 2n plus 1 by 2 x divided by 2n plus 1 by 2. Okay. Now I can simply insert the limits in this expression, and this will become, if I insert the limits, it will become 1 over 2 pi two over 2n minus 1 sine the upper limit, that is 2 pi. If I insert that, it will be something like this, minus the lower limit, that is 0, minus the denominator from the second expression and the limits. Okay, so as you can see from this, sine 2n minus 1 pi will be 0, sine 0 is 0, sine 2n plus 1 pi is 0, and sine 0 is 0. So overall this bn is 0. Okay, and your an was minus 4 root 2. If you see from previous pages, 4n square minus 1, and the value of a naught was 4 root 2 over pi. So you simply have to insert these values of this Fourier coefficient into this Fourier series extension, and the function which was originally root 1 minus cos x and which was equivalent to root 2 sine x by 2. This function is equivalent to the Fourier series expansion for this function is 2 root 2 over pi, because it was a naught by 2. So a naught by 2 will be 2 root 2 by pi minus this minus an minus 4 root 2 over pi summation n the cos nx upon 4n square minus 1. So you can say this will be 2 root 2 over pi minus 4 root 2 over pi. If I insert 1, then it will be cos x divided by, it will be 3, right? It will be 3 plus cos 2x divided by 4 into 4 16 minus 1 is 50 plus cos 3x divided by 35. So in this case, you are also you're also supposed to find identity, and you're supposed to find the value of one over 1.3 plus 1 over 3.5 plus 1 over 5.7. Okay. So for that identity, if you simply insert the value of x is equal to 0, value of x is equal to 0, then this identity can be solved very easily. Okay. Now, this thing you have to understand that why I am inserting x is equal to 0 here. See, as I can see from this expression, this is 3, 15, 35. So I am getting it is 1.3, it is 3.5, it is 5.7. So I am getting my identity from this, but in numerator it should be 1. Okay, in numerator it should be 1, and cos is 1 at 0. So if I insert x is equal to 0, then all the numerators will be 1. Okay, and the denominators are looking like this one. And if I insert x is equal to 0 in my left hand side, it will become, okay, so my left hand side, if I insert x is equal to 0, it will be 0. Okay, and it will be 2 root 2 over pi minus 4 root 2 over pi, and this whole series. Okay, so if I rearrange these terms, it will be this series is equal to, it will be equal to half. Okay, ये 2 root 2 इस तरफ आ जाएगा, and it will be half. So the value of this series I can find with the help of this Fourier series expansion of this function, and it is coming out to be half. Okay. So these two particular problems, along with that linear function expansion fx is equal to x, and along with x square in the range 0 to 2 pi, of course, these four problems are actually the basic problems which you should do, and of course some related problems also. Sometimes they ask for a basic problem also. Okay, so the next property about the functions which we will be using in this Fourier series is actually a very important property. Okay, see, you must have heard about the even and odd functions. Okay,
Yes.
if we know about the nature of the function, whether it is even function or it is odd function, if we can establish the nature of the function, then actually it is very helpful in calculation of our Fourier coefficients. So a even function, any function fx is said to be even if it is following this property. Okay. Fx is equal to f of minus x. Okay. Then that particular function, we can say this function is even function or symmetric function. Now, why it is called symmetric function? Because the graph of a even function is symmetrical with respect to y-axis. graph of an even function is symmetrical with respect to a y-axis. For example, let's take a simplest function fx is equal to x square. So if I insert minus x instead of x in the function, then you can see this function is not changing. So yes, this is a even function, x square is a even function, and if I plot this function, then it will look something like this. Okay, let's say I am plotting this function from minus pi to plus pi. Okay, and this is the value of the function itself. This is fx, and these are fc sub, that is x. So this even function, as it is symmetric around the y-axis, as this function, if it is even, then it must be symmetric around the y-axis. So what does this mean is? See, this area under the curve, is actually will be equal to this area under the curve. This area, this blue shaded region, will have same area as this orange shaded region. Okay, so I can write, so what I can write is, for this particular case, when function is even, area under curve from minus pi to 0 is equal to area under curve from 0 to pi. Okay, so what I can do is, if a function is even function, then I can simply write the integration of this function from limit minus pi to pi. We can simply convert the limits of this function from 0 to pi and fx dx. Okay, as you can see, the total area under the curve will equal to the twice of 0 to pi fx dx. And of course, in any case, if you require this much, this particular type of thing, then it will also be equal to this one. Okay, so as or in general, it can from a to minus a to a, and it can from 0 to a. Is even pi is not necessary here, but in our case, mostly in our problems, in the problems which we are be dealing with, mostly it is pi. So yes, if a function is even, we can simply change the limits. Okay, we can simply change the limits from minus pi to 0 to pi. Now this particular property actually helps us in reducing the steps when we are inserting the limits. Okay, for example, in any function, generally when you insert 0 instead of minus pi, when you insert 0 instead of minus pi as a lower limit, then the function or the expression simplify early. So this was all about the even functions. On the other hand, let's see what will happen if a function can be defined as odd function. So a function fx we can call the function fx as odd function if f of minus x, if we insert minus x instead of x in the function, then f of minus x gives us this value, minus fx. Okay. Then the function is odd function or skew symmetric. This odd function is also called skew symmetric. In this case, okay, let's take an example of a odd function. Let's say simplest odd function is your fx is equal to x. If you insert x minus x instead of x, okay, x भी है, x cube भी है, and all the odd powers, x instead of minus x instead of x, then it will become, you can say, f of minus x will become minus of fx. So if I plot this function, let's say if I can plot this fx is equal to x simply, fx is equal to x will be a straight line passing from the origin. Okay. Now you can see the area under the curve. Okay, this was your fx, this area under the curve is actually equal to in magnitude, but will have a negative sign with this. Okay, this area under the curves under blue shaded region and orange shaded region will be equal in magnitude, but yes, that will be of negative of this. So for this particular function, for a odd function, what I can write is area under curve from minus pi to pi, minus pi to 0 is equal to negative of area under curve from 0 to pi. Okay, so this particular property yields me a result that integration of a function from these limits from minus pi to pi of a odd function, the total integration will be equal to 0, because integration is nothing, integration is just the simply the area under the curve. So as the area under curve from minus pi to 0 is equal to negative of the area under curve from 0 to pi, 0 to pi, this was your minus pi, 0, and this was your pi. So these area under the curves are equal and opposite, so they will cancel each other. So the total integration from minus pi to pi will be 0 for a odd function. Okay. So
Sir,
yes,
sir, area under curve is taken between x-axis and line.
okay. Yes, I have drawn. Okay. Good. Yes, it should be horizontal way. Okay. It should be something like this. लास्ट में इवन में भी गलत किया था क्या?
नो सर।
No, sir.
Yes, sir.
Yes.
इवन में ठीक है। ओके, इवन में भी उल्टा होना चाहिए वैसे तो देखा जाए तो।
Yes, sir.
हाँ, इवन में भी उल्टा होना चाहिए। ठीक है, इसको ठीक कर
यस
लेना।
सर।
ये नोट्स में भी गलत होगा, फिर आपके जो पीडीएफ में भेजूंगा उसमें भी गलत होगा। ओके, गुड, वेरी गुड। ओके, सो I will utilize this. Okay, before going to an example, I will just want to state some properties that a odd function when multiplied by a odd function, then the resultant will be a even function. Similarly, even into even will be a even function, and odd into even will be a odd function. Okay, so based on the properties which we have discussed for even and odd functions, I can say that for even function, the Fourier series expansion or Fourier coefficients will be something like this. A naught is equal to, instead of now from minus pi to pi, I can simply write 0 to pi and twice of the function, twice of the integral. Similarly, an I have to calculate, because as function is even, fx is even, and the trigonometric function multiplied in case of an is cos nx, which is also a even function. Sin nx is odd function and cos nx is even function. So even multiplied by even will give me a even function. So I can simplify the limits only. I cannot make the integral equal to 0. But yes, in calculation for a, I can simplify the limits. But in case of bn, as if function is even, if the given function is even and sin nx is odd, so the overall, the multiplication of this function into sin nx will give me a odd function. And you know, a odd function in these limits minus pi to pi is equal to 0. But remember one thing, you can only apply these shortcuts or these properties when limits are from minus pi to pi. If limits are from 0 to 2 pi, you cannot make the integral of a odd function to be 0. Okay, you have to keep in mind this thing. Generally in exam, students क्या गलती करते हैं, लिमिट्स दिया होता है 0 to 2 pi, 0 to 2 pi and x square dx, या इवन फंक्शन कोई भी एक इवन फंक्शन दे रखा है x square cos x dx. Now this is a x square sin x है. Now this is overall, this function is odd function, so you can simply see this function is odd. Student mistakenly mark it 0, calculate it 0, but this is not the case. You can use this simplification only in the case when limits are given from minus pi to pi. Okay, in exam you will be having around 2 questions from Fourier series. In that questions you have to see if their limits are given from minus pi to pi, then of course they will be asking, they want to ask a question about the even or odd functions. If they are asking the limits from 0 to 2 pi, then it must be something else. Either they want to evaluate the Fourier series coefficients on a discontinuous function, or some other half range series, and that we will discuss later. But remember, for application of these properties, for application of these simplifications, the limits has to have minus pi to pi. Similarly, for an odd function, the simplification for an odd function, the simplification will be something like this. In this case, you can see, if as my function is odd, so this integral a naught will be 0, this integral an will be 0. Cos, if function is odd, then cos nx is, as cos nx is even, so it will be odd into even, that is that the total function fx cos nx will be odd function, and hence the integral will be 0. So there will be no an component, there will be no a naught component for a odd function. The only component will be bn, and even in that case we have simplified the limits from minus pi to pi, we have converted to 0 to pi. So for a odd function, now you can see, for a odd function it is very easy to evaluate the Fourier coefficients. A naught and an are 0, bn you have to calculate. Now if you look, okay, now this property I have shown to you now, but in first lecture I was solving fx is equal to x and fx is equal to x pair. In those cases, if I see, if you can see, yes, see, this was your odd function. Okay, in case of odd function, a naught fx is equal to x, a naught was coming to be 2 pi. Similarly, there will be some value. Okay, an was 0. Okay, an was 0, and bn was minus 2 in. So you can see, you can directly do this question by considering this function as odd. Okay, sorry, sorry. As the limits was 0 to 2 pi, so it has some changes. Okay. वो x square किसका किया हुआ है? Yes, x square जो किया हुआ है, that is in the limits. That is in the limits from minus pi to pi. So yes, we can use that application of this even function or odd function in this particular range. So if you can see, as this was a even function, so even functions का क्या property था? bn will be 0. Okay, a naught an you have to calculate, but bn will be 0. So if I see, yes, if I see, a naught was there, 2 by 3 pi square, an was there, 4 by n square minus 1 raised to the power. But yes, after calculation, after whole of this calculation, we have seen that bn is coming to be 0. So this thing, in this particular question, yes, you can use that property. If limits are from minus pi to pi and function is even, then the bn coefficient will be 0. Similarly, if suppose it was x cube from the same limits, with the same limit, if the function is x cube, that means the function is odd, then a naught and an will become 0 automatically, and you just have to calculate the value of bn. Okay. Okay. So, okay, from this exercise, I have solved question A and question C. Now, for question B, as the limits are from minus pi to pi, and this function is neither even nor odd, a function cannot be, you cannot tell the nature of a function when there is a addition or subtraction of two different type of functions. You can only tell when they are multiplied. Okay, odd into odd is even, but odd plus even, you cannot tell how this function will behave. But yes, these property will be helpful to you in the respective integrals. Okay, this I will show you just with the example how this property will be helpful. Okay, so let's take an example. This will be last question for today's class. Okay. Let's, with the help of these even and odd function properties, we want to solve a function x minus x square from minus pi to pi. Okay. So for you cannot tell the exact nature of this function, whether it will be an odd function, whether it will be a even function. So I will be calculating the value of a naught, that is 1 over pi minus pi to pi fx dx. Minus pi to pi x dx minus 1 over pi minus pi to pi x square dx. ओके, x dx माइनस x square dx, मैंने इस फंक्शन को डाल के और इसको ओपन कर लिया इसको. नाउ दिस फंक्शन इज अ ओड फंक्शन and this function is a even function. So I can simply write, for this odd function my integral will become 0 and this will become minus 1 over pi, and I can also change the limits from 0 to pi, and I will take the double of this integral, that is x square dx. So it will become minus 2 over pi x cube by 3 from limits pi to 0. Now see, I have changed the limits from minus pi to pi, and now I am writing 0 to pi, and it will become minus 2 over pi cube by 3, and it will be minus 0. It will be minus 0. So I am neglecting that. So it will be, the value of a naught will be equal to minus 2 by 3 pi square. Okay. Similarly, if I want to calculate the value of an, if I want to calculate value of an 1 over pi from minus pi to pi fx cos nx dx, and it will be x cos nx minus 1 over pi x square cos nx dx. Okay, so this you can see, this particular is odd function, this is even function. So that this function is particularly, you can say, is a odd function. Okay, and this particular is your even function. So I will not bother about this function. It will simply, this integral will simply become 0. And for this even function, I will change my limits. This an will become minus 2 over pi from 0 to pi. Now I have changed the limits and I have taken a 2 in numerator. X square cos nx dx. Now I will simply apply the chain rule. I will simply apply the chain rule to solve this integral. An will become minus 2 over pi. Chain rule was first function as it is, differentiation of second function, integration of second function, minus differentiation of this term, this will be 2x, integration of this term, this will be sine minus cos nx by n square now. Okay, one n from the previous step and one n from the current step, plus differentiation of this term, that will be 2, and integration of this one, that will be minus sine nx divided by n cube, minus differentiation of this term, that will be 0. Okay, and all next terms will be 0. So see, from this expression, okay, and limits were from 0 to pi. From this expression, what I can see is, if I insert pi and 0, if I insert pi and 0 in this term, then it is going to be 0. Both the terms will be going to be 0. Similarly, in this sine nx, if I insert pi and 0 limits, both these terms will be 0. But yes, you have to do that. You have to show that after inserting the upper limit and lower limit, these two expressions are going to be 0. Okay. And the only term which will remain after inserting the limits will this one. So I will solve this term. It will be minus 4 by pi n square x cos nx pi to 0. Okay. So if I insert the limits also, then it will be minus 4 by pi n square. It will be pi cos n pi. And the second term, after inserting the lower limit, this 0 if we insert, then in this x will become 0. Okay. So only the first upper limit will remain. Now you can appreciate the beauty of this limit changing, that if I have converted minus pi to pi to 0 to pi, now see, if I am inserting this 0, then it is simplifying the expression. Okay. Otherwise, agar pi and minus pi hota, then there will also be a second term, minus pi something, and of course that will be a twice of that, but you have to, in some longer functions, you have to actually manually put the minus pi limit. But in this case, it is simplifying on its own. So this pi will cancel out from numerator and denominator, and this an will become minus 4 by n, and cos n pi is minus 1 raised to the power n. Okay. It is n square. So an will become this one. Okay. So the last Fourier coefficient which I have to calculate is my Bn, and it will become 1 over pi minus pi to pi x minus x square sine nx dx. So if I open this integral, this will be 1 over pi minus pi to pi x sine nx dx minus 1 over pi x square sine nx dx. Now you can see this function is even, this function is odd, so the overall function will become odd and hence it will be 0. Similarly, this function is odd and this function is odd, so the total resultant of this function will be even. So I just have to calculate this integral and this integral will go to 0 on its own. So this Bn will become 1 over pi. Okay, I am also changing the limits here. So this Bn will become 0 to pi. I am changing the limits only when my function is defined and it is even. Okay, this function x sine x is defined as even, it can be defined as even, then only I am changing the limits minus pi to pi to 0 to pi. Okay, it will be x sine nx dx. So if I integrate this again by using chain rule, I can integrate this. Bn is equal to 2 over pi, the first function as it is, and the differentiation integration of second function cos nx by n minus the differentiation of first function, that will be 1, and integration of this function minus sine nx by n square, now 1n from the previous term and 1n from the current term, and limits are of course from 0 to pi. See, in this case also you can see this particular term will go to 0 when you insert the limits pi as well as 0. Sin n pi is also 0 and sin 0 is also 0. So you can just leave this term, and if you insert the limits in first term, that is okay, n भी बाहर ले आते हैं, minus भी बाहर ले आते हैं, this will be x cos nx in limits 0 to pi. So minus 2 over n pi, it will be pi cos n pi minus 0. Okay, it will be pi cos n pi minus 0, and this pi over pi will cancel with each other, and the value of Bn will become minus 2 over n cos n pi, and cos n pi is minus 1 raised to the power n, minus 2 over n minus 1 raised to the power n. Okay, so now I have calculated all my Fourier coefficients, and I can simply insert this Fourier coefficient into my Fourier series expansion. X minus x square 1 by 2, and the value of a naught was minus 2 by 3 pi square plus summation n minus 4 by n square minus 1 raised to the power n, and of course the cos nx. This was my value for an, plus summation n minus 2 by n minus 1 raised to the power n sin nx. So if I insert this summation, if I open this summation, it will be okay. The first term will be simply minus pi square by 3. Okay, and this 4 I am taking as common from this expression only. From this expression only, minus 4, and if I insert n is equal to 1, then it will be 1 by 1 square, and if n is equal to 1, then it will be minus 1. Okay, and so it will be minus cos x. The first term corresponding to n is equal to 1 will be minus cos x. Similarly, second term will be 1 by n square, so it will be 1 by 2 square. Okay, simply write 1 by 2 square, and it will be cos 2x. Now minus 1 raised to the power 2 is plus 1. Similarly, again a negative term, cos 3x, and so on. So basically, this minus 1 raised to the power n, whenever you see this in the summation, this minus 1 raised to the power n will do only this thing. The first term will be negative, and the positive and negative will be alternate. First term will be negative, second will be positive, third will be negative, fourth will be positive. So this minus 1 raised to the power n is doing this. And for sine terms, it will be, if I take out the common, okay, if I take out the common, it will be minus 2 minus sine nx. Again, there is minus 1 raised to the power n, so there will be an alternate plus and minus sign in the terms, starting from negative. Sine x plus sine 2x by 2 minus sine 3x by 3. Okay, so for this solution, for this particular function, the corresponding Fourier series will be this much. Again, you can always check the validity of this Fourier series analysis by plotting the graphs. Okay, if you plot x minus x square from minus pi to pi, and if you plot a single function, which is this one, this whole function, then of course the graphs for that function will match in the particular limits. Okay, वो आप कर सकते हैं उससे जो पिछला क्लास में हमने फंक्शन बना के दिखाया था. Okay, so in next class I will be giving 1 or 2 more examples about this even and odd functions, and after that we will move to the discontinuous functions, see how we can express the Fourier series expansion of a discontinuous function. Okay, so in next class we will see one or two more examples of this even or odd function properties.